Hello students, in the previous lectures we have discussed how to find the higher order derivative, that is second order derivative, third order derivative, fourth order derivative and so on. So we and also we know that we can find the higher order second order derivative if the first order derivative, the function after finding the first second derivative is continuous, then we find the higher derivative if different and so on, third order and so on. Now in this lecture we'll use the concept of finding the higher order derivative to find the nth order derivative and reduce with the help of mathematical fundamental mathematics we'll find the nth order derivative of some standard functions, and after in the next lecture we'll use these results to find to solve problem based on it, right? So let's find first function. If y is a function of this linear function ax to b is by n, if x y is of type linear function is called m, then any derivative of y will be equal to m into m minus 1, m minus 2, m into m minus n plus 1 into ax to b is power m minus n. Now, one method we have by the fundamental principle of explanation, other method we can generalize it. We find the first derivative, then second derivative, third derivative, fourth derivative, and fifth derivative, and then generalize them. We find the successive derivatives. We have two methods to find the no derivative. We find the first derivative given for the second, third, fourth, fifth, and generalize that to the derivative. Or second is by the fundamental principle of mathematics. What is fundamental mathematics? Will show that result is equal to 1, assume that result is equal to k, and prove that result is equal to k plus 1. Now, this implies if result is equal to k, we have proved that it is equal to k plus 1. So, if k is very large number, so very large number plus 1 is result is also equal to very large number plus 1. So, what does it imply? It implies that it is for all positive. So, I have told you about the fundamental principle of mathematics in this problem. We use it in the every nth order derivative. We got to deduce in this lecture, right? So you we will not cancel out the comparator. We'll standardize it while finding this derivative. We'll standardize it and compare with the nth derivative given in derivative, or if nth order derivative not given, we'll prove it by finding the successive first, second, third, fourth, and then. If nth order derivative is not given, you are just asked to find the derivative. You will find the successive order derivative and generalize that to the nth. You will find so let's take this problem. So here ny is equal to ax to b square. Differentiate this way. Differentiate this. So this is equal to m ax to b raised to power m minus 1 dx of ax to b. Now put L is equal to 1 this. Is equal to 1, minus 9 is equal to 1, equal to m minus 1, is for 1, and it will be n. Implies that if you that is 2 by into 2. Now let's assume that the result is true for n equal to k. That is, you place n by, you just place n by k. K is equal to k and plus k. Now you have assumed this is true. Now our aim is to show the result is 2 by equal to k plus 1. Now differentiate this. So this is to k, this to x, sorry. So differentiate this is equal to k plus 1, and this is to x. By k plus 1 is equal to the constant and outside differentiate this. This will be equal to how much this? This will be differentiate this. This is equal to k minus 1 n minus n minus k. So what can n minus k n minus k into this and this the k is here. Is okay, you get from the differential of this into this. So this is here. Differentiate this a into m minus k minus 1 and m minus k, and now standardize it. What will be this become? It's equal to m minus 1 means m minus k ax to b is power minus k plus 1 is power k plus 1. Now replace n by k plus 1 here. You get the same result. Same result. Like that is equal to k plus 1. Now the result is for all. How the result is for and always n? We have assumed that it is for k and it's proved that it is k plus 1. However large k may be, k result is for k plus 1. This implies what we have proved that is for k, and this implies that it is for all positive. Same process will apply. Okay. Now next corollary based on this. If m is greater than the same, the result we have produced, this result we have produced will multiply the numerator and divide by this. We got yn and it is equal to m into n minus 1, m minus 2, m minus n plus 1, ax is equal to minus n is multiply this numerator, cancel out. Now this will become m minus 1, m minus 1, m minus n plus 1, m minus n plus 2, and so to m. So this will become m factorial upon n minus m factorial into ax will be square m minus n square. So n derivatives. If m become equal to n, if m become to n is equal to n, then m is equal to n, this is equal to, we can write m factorial or n factorial. M minus n 0, j factorial is equal to 1, or m is equal to n, this is equal to m minus n is equal to 0, m minus n, m is equal to n, and you can place m by n or m by n. Is for n factorial is n. If m, if we'll find the same order derivative, so we get factorial is that number, and factorial is for m or n factorial is for m, right? If n is greater than m, power of the function is exponential function is less than the derivative, then the higher derivative will become 0. Now, next slide. Similar way, in similar way, drive it. Y is equal to 1 upon x plus b, then y and any derivative y is equal to minus 2 for n, and factorial a is for n upon ax is for n plus 1. For this should not be equal. This will be, zero means ax should not be equal to minus b, or x should not be equal to minus. Then this will be 0. If it denominator becomes 0, this becomes undefined. So we have written this point, that point is 0. Same process. When is given, differentiate with 2x. So this is equal to, now again ax to p raised to power minus 1. Same formula. And x square minus 1. Derivative chain rule. Standardize that. Minus 1 into a upon this. X to p raised to first derivative. Now put n is equal to 1. Same process. Put n equal to 1. The standard result equal to 1. We got the same value implies, which is the same as the second, implies derivative equal to 1. Assume result is equal to k. Replace n by k, and the differentiate test is 2k. Differentiate this constant, this is constant, this is constant. Differentiate this will be, this is minus k minus 1. X to be raised to n minus 2 into differentiate this chain rule, right? Constant outside. Now again put the value n equal to k plus 1 here, k plus 1. So k plus 1 here, differentiate this. So, form. So after this, we got this k plus 1. So this will be same. If I put into change given result, you will get the same result. Implies result is equal to k plus 1. And by the method visual reduction, result is for we have shown result is equal to k, and the 1, and we assume that is equal to k and prove that result is equal to k plus 1, and so the result is for all values of n by the fundamental principle of mathematics. Again, same process. Y is equal to log of x plus b, and y n is equal to this. Let prove for n for x is greater than x is greater than b upon a. Log of negative is not defined. That's why we have written x is greater than this. Now x should be greater than for this to be defined. So we have impose the condition. This should not become undefined. This and y is for is y is equal to for x, and there is this y is equal to ax, and there is this y is for mx, there will be this y is for ax. So similarly you can put these results, same process for these results, so you can put these results yourself. Now let's try another results. Y is equal to sine of x plus b. If y is equal to sine of b, yn is equal to a by n sine of x plus b is equal plus n pi by 2 for n belongs to x equals to r. Now again, first same step, y1 is given, reduction, differentiate this to x, proof same by fundamental principle of reduction. Differentiate this, cos, convert that into same sine is equal to, or put n is equal to 1. Here we got this, and there is the same one that here. I am here, this is 1, we got y in film, that is equal to 1, assume that is equal to k. Now differentiate that is to k with x. So differentiate this is equal to k plus 1, this is k, differentiate this is equal to sine cos into a, cos convert that into sine, and put n is equal to k plus 1 here. Here you get the same result here, and say the result is equal to k plus 1. Assume result is equal to 1, and the result is equal to k, and 2 result is equal to k plus 1. Hence, by the principle of multiplication, result is equal for all integers of the z. Similarly, you can prove for y is equal to ax plus b. If y is equal to x plus b, then yn is equal to a by n cos of ax plus b by n by 2 x equals to 1. Right? Similarly, as we did structure. Now, again, if y is equal to e is for ax sine of bx plus c, then yn is equal to a square plus b square base by 2 e for ax sine of bx plus c, bx plus c. This is c, not b. Bx plus c, bx plus c plus 10 and 10 inverse of bn. Again by c. Let us prove y is equal to this. So y is equal to this. Differentiate this with x. We have to prove this equal to this. By this, we have to prove this equal to this. So again, we perform the integration. Differentiate this with x. Same procedure. Differentiate with x. Got this. First function, third function, and now convert that. Now we are trying to convert into sines in terms of sine form. So this is equal to, we have made a substitution. Let's now to combine. We're going to combine this. This is special step. If we take a is equal to r cos theta and b is equal to r sin theta, you want, why we are supposing this? You want to convert it into sine, same form, sine. This is equal to sine of this. This is sine of this. That's why you assumed it here. R cos theta, R sin A cos B plus cos A sin B is equal to sin of A plus B. Converting that, that's why we are making this expression, and we'll find the value of R and alpha, and both values we can find here. A is equal to R cos alpha, B is equal to R sin alpha. Substitute the values here, A and B. Then what will be R? Squaring and adding first and second, we got R is equal to under root of A square to B square, and dividing second by first, this is tan alpha is equal to Japone alpha is equal to tan square. So we know substitution, we know the value of R and alpha in terms of A and B. These numbers are known to us. So after substitution, there are cos alpha and R sin alpha. R comes out in common, and this will be sin A cos B plus cos A sin B, sin of A plus B. So why we did this? We have to convert. This was sine function, derivative function. That is a sine function. That's why. Similarly, you can do. You have to do in the cos. If you do this cos, you have to convert in a cos formula. It makes a substitution in such a way so it becomes cos. This is equal to A is equal to cos A cos B cos plus sin B, cos A plus B. It comes into cos is equal to R cos theta, B is equal to R cos theta, A is equal to B is equal to R cos theta, A is equal to R sin cos theta. Right? So after coming this, put the different type. So we got result. So now make substitution y is equal to 1 here. Y is equal to n equal to 1 here. After substitution we got the same. Implies that this equals to 1. So got we got result is equal to got. So then we got the result is equal to 1. Okay. Now let's assume the result is equal to k. That is replace n by k. Now differentiate the n by k. Convert that into r and into r. Otherwise you r and differentiate these two. Now this is very important step. If you differentiate it, if you not convert them to R and alpha, you find it difficult to keep this step in mind. Differentiate this with this to x. Differentiate this with x. So for that, you have to convert that into R and alpha. So differentiate x is a function of R is equal to R is for ax common is for ax, b cos of bx for c, a is for x, sin of this. Now is for x is common. Common is common step is outside. Put the value of a and p here again. Same process as in the derivative first order. Now again we have formula to side. Same formula will be used here. Is equal to r we have taken out. R plus 1 is for x is equal to sin a plus sin a cos b plus cos a sin b sin of this b a plus b is equal to k plus 1, and again substitute every parameter here. We got the equal to k plus 1. To check, we can check it first through. So n plus 1 k plus 1 derivative of the given function is. Now in order to check it, this is 2. We'll go to the n derivative of this. N derivative of this is this, and this, and put in place of n we put k plus 1, and we will got the same result. Same result here. Same result here. This is same result. Implies result is 2 for n is equal to k plus 1. Now we have proved result is 2 n is equal to k, and assume result is true for k n is equal to 2. We have proved result is n equal to 1, and assume result is 2 n is equal to k, and prove that result is n equal to k plus 1. Hence the result is true for all positive integers. In the similar way, you can find the if y is equal to e square x cos of bx plus c, then we can find y any derivative is equal to a square plus b square is equal to 2 e power ax cos of bx plus c plus n the inverse of b upon a. Here difference is only we convert, in place of converting this we converted this into sine. In place of the first derivative as well as the k% derivative, we have converted this in sine. Now in place of cos we convert that into cos. We make substitution a and b such a way so that this will become cos of a plus b because the function is cos function. So in the similar way we can do this. Thank you.